Do you see the correct screen?
Yes, but I think because of your double screen, we actually see both the slides and the next slide and the comments.
Okay, so I should swap.
Yeah, it usually happens to me. Yes, now we only see your full screen. Yes, thank you.
Okay. Yeah, it's a bit. Do you see where I'm? Oh, okay.
Yes,
okay.
yes, we see.
Okay.
Yeah, we might not see everyone, but we see
No,
you.
no, it's okay. I wasn't sure if I was. Well, this is a sort of a type of because I don't see where the camera is pointing. So that's why if I look at you, I don't look at the camera.
Yeah.
So that's it's a sort of type of.
Yeah.
But anyway, let's go. So yes, thanks for having me. I'm Luca Podofillini from Porsche Institute, and I will talk to you about some of the expert judgment issues that we have in human reliability specifically. The models we develop and some of the examples that we approach, how we approached collecting data and collecting specifically data from expert judgment. So a little bit of where I work. I am within a laboratory, which is called Energy Systems Analysis, and it's a quite large laboratory, including 4 research groups. I mean one, we have 4 research groups. We actually belong to 2 different research departments, if you will, the general energy, so we deal with, and the nuclear energy. So our approach is really analyzing energy systems with a large perspective, environmental risk. We have energy economic group specialists, so that's also the economics, social aspects, and we develop tools and recommendations for future scenarios, future energy mixes in how to meet CO2 net zero scenarios and so forth. My group, or the group I'm working on, specifically deals with nuclear safety, so more on probabilistic risk analysis with a bit more focus on nuclear and then a little bit more focus on human reliability. The reason of this double focus is in a way because our group is actually relatively small, so this is the whole lab with the various groups that, as mentioned, deal with different aspects. Our group is actually quite small, so that's why also this double focus on nuclear and human. But we are starting to grow and dealing also with non-nuclear safety, of course. Non-nuclear application, more on general energy, and also, of course, resilience applications, and not just the risk analysis by the book. So, with more focus on this talk, yes, the focus will be on human reliability. And okay, the excuse to talk about expert judgment, elicitation, and issues are 2 applications. One is on a radiotherapy model for human reliability that we developed. It's not very recent. I mean, it's also not quite old, but it's not really very recent. And the reason I bring it up is, on the one hand, because we really went to the experts and elicit, values from them, and we didn't really have a lot of experience on doing this. So it was quite interesting for us, and also, it's also good to share these practical experience that we had. The second reason is because one of the students that was involved into this group, the larger work or part of the work was done within a PhD. So the student went, maybe now 5 or 4 years ago, at the beginning of his study, in one of the seminars that were organized within this expert in uncertainty cost action, where I can see in the distribution list many of the people were involved. So it's also nice to see how the student came back and actually applied what was what was learned in that workshop. It was in Madrid, I think 2016 or something like that. So the second part will be more on the models, so Bayesian belief networks, and how we have to develop, we try to develop them with the little data that we have, and also combining with expert judgment. During the application, generally, we try to validate the models that we have. And this is something that, especially when you see risk analysis, but probably not in the group not in the audience today, but in general, when you see a lot of risk assessments or even Bayesian belief networks application, there's not a lot of emphasis on validation. Try to find the reasons on, okay, I mean, can we believe the number that we come up? So, of course, it's not going to be hardcore validation, but I'm going to show you every time how we actually try to reply to this issue. So concerning human reliability analysis, to give you just a little focus, I mean, I'm not going too much into detail, but I just want to focus on the types of models. No? Human reliability, HRA, is risk analysis, so scenario analysis, probability quantification, or likelihood, if you want to broaden it, and analyzing of the consequences. So the typical triplet with focus on humans, and within, generally a larger system that you're generally analyzing, which could be, your aircraft or nuclear power plant or whatever. So the analysis we make, this is really important for what's coming afterwards. The analysis we make are scenario specific. So, we really focus on sets of specific scenarios that may come from a larger probabilistic safety assessment model, or that we decide for other reasons that have to be analyzed, and they're very specific. So, low visibility because fog and rain, and an aircraft has landed but has not cleared the runway. So traffic controller needs to note the runway is not clear, and maybe communicate with the pilot. So what can go wrong, how likely is it scenario, and the possible issues that come up, and what are the consequences. So very specific. And we have a set of analysis, or we perform a set of analysis. In general, they are qualitative. So really meant to understand the scenario, the performance context. And these are generally in common with human factors method. And we're not going to talk about this too much, but it's important to contextualize, because we don't come up with models that are abstract. We really analyze specific situations, and then the models are helping us to actually come up with maybe human failure probabilities, or come up with recommendations. But underlying the model, there's always detailed analysis of qualitative of the context and what is the situation. But this said, as I said, the focus will be on how to develop the models. Now, models have been evolving since maybe 50 years. The grandfather of human reliability is this human method that is called the THRP, but then, has evolved over time. It has evolved because of safety science has evolved, so the role of humans, or the role of how to understand human error, human failures, all this issue of what is an error, what is a failure, and also the contribution of humans in the system has changed. So that has also involved changes in how these models are structured, and also cognitive science, of course, has advanced. So what is important for humans have evolved. But what is common, and what is really typical across all these models, that you have categorical factors, categorical variables that describe types of the tasks, which could be, noticing an alarm, monitoring a parameter, recognizing, taking a decision, types of tasks, quality of stuff, you know, interface, procedural guidance, you know, tools that are used. So, you know, aspects that are factors that characterize the way in which the context in which the task is carried out. And for example, time available, you know, how adequate is time for doing things. So in a way, common aspects of the methods are these types of categorical variables that you need to characterize. And that has an implication on how you collect data, what type of data you collect, and also how you collect data from expert judgment too. And I'm coming back on this. So the example that I mentioned to you is a model that we developed for radiotherapy applications that I mentioned. You know, I'm not giving you too much of the background, or we can discuss it if it's interesting later. But basically, we had a collaboration with, or we still having, with a radiotherapy facility at our institute, PSI, the Center for Proton Therapy, and they were interested in improving their safety analysis. Basically. They do have qualitative analysis, they do have analysis of retrospective events, but they wanted to make it more prospective analysis and quantitative, you know, for prioritization and that type of element. So we developed a human reliability analysis method to help them during this for this analysis, and the method looks like, I mean, I'm not going into the detail. I just wanted to focus on, you know, the element. So you have, as I was telling you, some types of tasks, checking quality check of some analysis, for example. So the task is for the personnel to check, for example, the output of a software, you know, in a therapy plan. So you will need to recognize that the value of the software is incorrect compared to what the expectation might be. So types of tasks, generic, categorical, if you want. Then clarity of the information, you know, whether this is mostly the layout on the numbers of the screen, whether there are interruptions, as you perform the work, and whether there's, for example, low vigilance during the error. Since this talk is more on the quantification and on the numbers, I'm not going to tell you much about how we develop this set. We have developed, in a way, a systematic approach for identifying important tasks and identifying the influencing factors, identifying these specific negative conditions that you have to analyze for each factors, and that's presented here. What is interesting is that this method is actually quite generic. So our idea in this work was to develop a meta method, you know, a method to develop a method. So how to identify the risk critical tasks and how to identify risk critical factors and how to really how to develop an HRA method. So what we were interested in is actually, as an analyst, would go through these trees. This is the task I'm interested in. I select, I first analyze whether the information is unclear. I have a couple of examples to check whether, you know, values on the screen are readable or whether there's some overcrowding information on the screen. And then if I go yes, I go here, and then, you know, blah, blah, blah. I get to the end. Here, the method should tell me what value, what probability to put in my overall system model. You know, often these models enter into larger, for example, probabilistic safety assessment. So, you know, it's going to be an input on a larger model of the whole system. So the way to get to these numbers, we had access to 12 workers at the Center for Proton Therapy. I mean, these had different background, doctors, medical physicists, technicians, ideas that were bad, and we knew that they were bad. Of course, asking questions, what is the failure probability in a quality check task in case of information unclear? You know, the way I'm going is, these are very theoretical expressions. So we will never be able to get any sensible and meaningful answer from this abstract concept. Even worse idea, if since we're interested into this branching, how would the probability change in case the information becomes unclear? So this is even more abstract. In many applications, I've also seen there are, and this connects with some application of method in multi-criteria decision making as applied when applied to human reliability analysis, where it's asked to the expert to say, for example, whether information clarity is more important than than workload, to rate, importance in the two factors. Again, still, I believe that it's very abstract and very different from for experts to do this, although you can see it in several works. So what strategy we adopted was to come up with specific situations to talk to the experts, coming up with failure situations to contextualize the information that we're interested in. And therefore, example situations, okay, these are of course clear application specific, given correct values on the control documents, how difficult it is to recognize mistakes on, coordinates that come up from the computer tomography, and to recognize that these are not matching. And when you formulate questions like this or situations like this, the person really starts thinking about, okay, what do I need to do? What is influencing? Yes, the phone keeps ringing, and yes, it happened to me once that I didn't notice because the picture was flipped. So that type of discussions that came up. And besides being able to provide you some not numbers, because then we are working on a qualitative scale, as I will tell you afterwards. But besides providing you this or input to the model, if you want, it's going to help them also to discuss issues in their current work. And I go back on this because we are really talking about specific situations. I mentioned interruptions, I mentioned background noise, and the like. So anyway, what we were trying to get from the experts is what is the impact, low, moderate, high, or very extreme of some negative conditions on the performance of the task. That's it. So that's what we believe that was sensible to ask. And as an example, for example, this is an example. I mean, what is the impact of values not being readable or of overcrowded information on the screen? Then we have 3 experts, for example, one said low, one said high, one said medium, and that's how we get. So we use this information of this failure situation and these specific inputs or situations to inform the decision tree, one of the set of decision trees that we had on the quality check that represent the task that is enveloped by this situation and the branching point information unclear. So we came up with around 10 failure situations covering all of the task types. We had about 6 types of tasks. And then for each of the 10 situations, we had 2-3 failure situations that we were discussing. So not every expert was asked to evaluate 10 situations because, the situation had different type of, we're covering different types of tasks. And, what the medical physicist does is different from what the technician does, and is different from what the what the medical doctor would do. So everybody was analyzing, yes, 2 or 3 failure situations with some branching situations. So not in the end, you know, every person was involved for about, well, depending, more than 1 hour, less than 2. So basically, that's what that's what was the workload that was involved. So now, how to convert this into a quantitative scale? So we use this correspondence. For us, low impact means very low failure probability. Moderate means 1 in 100, high means 1 in 10, and extreme impact means you're going for sure to fail. This correspondence is quite makes sense in one sense, but it's also quite common in human reliability analysis. I'm giving you the reference here, but it's actually quite common to learn about what is a likely failure probability, what is unlikely. So, you know, unlikely is somewhere 10 to the minus, very unlikely is somewhere 10 to the minus 3, and that's the scale that comes out. So in the end, what we did was to convert these statements into evidence of the order of magnitude of what the probability will be, and so and then you need to plug it into the model. Order of magnitude is really an important aspect because, you know, in human reliability, in risk assessment, if you want, or depending on the applications, we're of course not interested into exact numbers. We're interested into learning whether a situation is highly leading to failures or very challenging, or you know, you're not going to believe that any problem would occur. So really having a sort of a scale of difficulty as opposed to precise numbers. So we have this correspondence between the qualitative scale and so quantitative scale, and then we had to develop a way to aggregate basically the various judgments across the experts. And we developed, I mean, this was, it's a Bayesian update, you know, some of the might be fully clear, you know, starts from a prior, and then an expert comes in and says, it's moderate, so you believe in moderate peaks, and then the other goes down. So, you know, it's quite classical, except for a little thing that I will tell you after. So, you know, overall, it's really classical. So very traces back from relatively old times. We have specified this type of approach for human reliability analysis, but it's really what you would expect. So this is the example. As I said, you know, this type of task, if you want, this type of branching, and then for each of the possible negative conditions, we have different experts telling us different things. And then with our Bayesian approach, we update our belief on where the failure probability is. So this, as you see, I mean, this is a bit small, so this became orders of magnitude, 10 to the minus 3 to 1. And underlying, there's an assumption of how likely it is that the expert would give you the correct order of magnitude. So we assume that 80% of the time will give you the correct order of magnitude at least. So, you know, that would enter the likelihood of the Bayesian update. And so that's how we aggregate horizontal. Now the issue is how to then aggregate vertically. So vertically, you know, we need to have an aggregation also along these lines to also to learn about the branch, you know, because the branch includes multiple conditions horizontally. So again, relatively classical Bayesian update, but instead of learning getting information from the expert on the mean or on the median in this case, we assume that each of these negative conditions are members of a population of a different of a statistical population with different basically, so they have different means. So basically what we are learning is the distribution of the various means across this direction. So in this way, we on the one hand consider the uncertainty from the experts, because different experts will give us different values and different beliefs on that, but also the variability. And because negative conditions can be different. The issue of variability and how to consider that in especially in human reliability is actually quite important and really often neglected, in a way that whenever people collect data or expert judgment, you see that in many cases all these statements are lumped into one evidence, into one pool, which basically means that you often see results that have a super narrow uncertainty, because if you pull everything into one pool, if you will, if you are learning one mean, then the mean becomes extremely solid, and therefore the uncertainty becomes a very unrealistic for the situation we're talking about. So I mean, I don't have examples on this, but we've been working quite a lot also on data, not just on the expert judgment, but also on data and how to preserve the variability across the data so that the uncertainty that comes out is meaningful, if you want. So back down to the results. Okay, these are some of the situations that we have elicited, aggregating in this level, and you see different types of tasks: interaction with software, determination of optimal parameters, patient's identification, with some negative conditions and impact. Some are higher, some are lower, of course. Comment number one, I'm not going too much on the details, I'm more on the model construction. Comment number one is, for example, what is the strongest impact? Complex interaction with tool in case of lack of training and experience. Now, if you see the graph, we have mission accomplished. No, we wanted to get numbers and we got numbers. So okay, then we're happy on the end of the branches, and we know what to put at the end of the branches. That's fine. But what is very important, and actually what maybe not surprisingly, what the people at Center for Proton Therapy appreciated the most was really the learning that came out on this exercise. So for them, this complex interaction with tool and lack of knowledge means that the underlying issue, for example, is that these centers, at least now things are of course changing, but these centers are often half clinics and half experimental centers, which means that the softwares are homemade. So if you come from a different facility, you have a software that 90% of the times works more or less the same, and that 10% of the time, maybe there are some tricky changes that you need to be aware of, and if you don't train people on that specific 10%, which probably you don't even know where the 10% is of difference, then you can get a serious consequence. And this was something that was really appreciated by the personnel, to know, to be able to come up, to emerge, to make this potential issue emerging with also potential interruptions, all these type of elements that were of course then appreciated by and considered by the management as well. So that's, you know, in the end, what, if you will, the double output of numbers and qualitative analysis that I was also mentioning at the beginning of introducing HRA. Now, you know, the funny validation, I promised, you know, to do some validation, you know, that's what we attempted, if you will. So we look at the literature, human reliability and human factors literature, finding numbers that we imagined that had some applicability on the task that we were considering. You know, we were considering checking numbers, we were considering, you know, exchanging information, looking at screens, copy and paste. And we found numbers from, yes, okay, you know, from HRA methods, and here you see from other methods, more generic methods. I mean, and here are the values that we believe have some applicability. So now you see, you know, this is what the experts came out. This is what the literature says. So, you know, exact matches along this line. This first band is a factor of 3 above or below. This is a factor of 5 among and below. And, you know, we were happy to see that you know, most of the points were in this factor 5, which for HRA is completely acceptable, because, you know, as I said, you know, we wanted to know what is difficult and what is not difficult. And it's interesting to see that the ones where they're very off, then we went back on the data and see where they're very off. And for example, we realized that some of these were clearly not applicable, you know, taken out of the context. So the red dots are, you know, for as an example, you know, we were matching tumor complexity recognition, you know, a complex tumor to be recognized with traffic complexity for air traffic management. So, you know, clearly they don't match, and that's why it's red, and that's why we were not surprising to see complete variations. But, you know, in the end, we thought that this was at least giving some credibility to the values that were, or some justice to the values that were coming out on the expert elicitation. So this is the first part of this work. And actually, Dhruv Pandya was the student who came in this workshop some years ago in the cost during the cost action. So I'm going to give you another flavor aspect on on our application of Bayesian belief networks instead. The context is okay. I'm not telling you why what are the BBNs, but the reason why we like BBNs, maybe it's more interesting for you. The reason why we like BBN in HRA, human reliability, is because generally classical methods consider these aspects of factors, influencing factors one at a time. You know, difficulty of a task, and then, okay, I sum on top of it clarity of information, and then I sum on top of it whether there's a shortage of time and so forth. But, you know, humans are not so simple machines, so things interact. So, you know, the effect, if you don't have a procedure for doing a task, if the task is super easy, you don't care about the procedure. If the task is difficult and you don't have a procedure for doing it, then the failure probability, you know, amplifies. So that's what I meant by, or that's what I would mean by not, you know, dependence across the effects and non-linearity across effects. And BBNs are actually quite good at dealing with this, and this is why we are working on that. We've been working on this extensively. So the specific application is, I'm not going too much in detail, but it's on errors of commission. So errors of commission are decision errors. And again, these are decisions, decisions are even more non-linear. You know, decisions are make you understand if you want, typical safety assessment is failure to do things that you were supposed to do. So failure to get to work by 8 o'clock. And then you analyze what can go wrong. Oh, well, I can get traffic jam, and the alarm doesn't work, and that type of I have a call on the way. So that type of things that linearly come up. Now decisions are even less linear because decisions are on the way to work. I decide that I'm going to the beach. So it's not like a sum of factors. It's a culmination of effects of, yesterday I had a bad day at work and my boss was angry, and today the sun is I had a bad night and it's a sunny day. So decisions are much more triggering events than what can a sum of things that can go wrong and prevent me to do things. So these are instead decisions that I made and makes things worse during an accident. That's it concerning the HRA part. Concerning the modeling, we have even less data. So what we have in our method to develop a method are two databases of operational events. So this was developed some years ago, including analyzing events that really happened at nuclear power plants that were analyzed, and then these were including events until year 2000 and so, and then this new publication, which is in the end is for like the last 20 years. These were analyzed by expert judgment, so there is some expert judgment, but there are real situations, real situations that we analyzed, and we want to feed into the into our models. So the analysis look like this. So these are event identifiers. The databases looked at this. Events identifiers. What has happened, it doesn't matter, and then factors, influencing factors. Doesn't matter what they really are. We don't have time to do this, and scorings, and then overall assessments of the situation by the expert. Very similar to what I had before. The error forcing impact of the situation. High, extremely high, low. That type of overarching analysis per each of the factors. And then there's also a correspondence between the label and the numbers, which is coming from different analysis that we don't have time to go over. But the idea was, okay, we have a set of 26 operational events analyzed in this time range, and we have a set of new events that have been developed or analyzed afterwards. Let's build the BBN on this. That's what the goal was, to be able to use, the concept is we want to have a tool that allows us to make predictive analysis as opposed to retrospective analysis. So we wanted to develop a tool that, based on assessments of input factors, would give us what the output is. Okay, bad ideas. Ask probabilities on all the conditional probability distributions. Ask probabilities on generic factors. What is the error forcing impact in case verification is is very high and time pressure is high. So you need to contextualize again. So the approach has been to get some of the relationships on from the operational event analysis, and then fill in the rest. We needed to have 250 conditional probability distributions. We had 30 operational events. So the 30 operational events were given some mapping, and then the rest you need to come up with something. So we developed a model, an algorithm to do this, and I will give you some sketches of how this algorithm looks like. Now, algorithms I'm not going to talk about the chapter of algorithms on developing BDNs with small data sets, but what was interesting for us was to, that's a simplification, maybe it's also because we wanted to find our niche for the paper. But you know, if you want, you know, you need to find a niche where there's no data, there's no stuff that has been done. But you know, you can really see that lots of work is on. Okay, you know, I have little data, but on practically all the CPDs. So you know, there are different variants, but the typical approach is okay. I have some priors. Then if I have data, I apply the prior. If I update the prior, if I don't have data, I will be happy with the prior. And then if I have little missing data here and there, I reconstruct the data that I don't have with some methods, but that's what the approach is. The other category that you can see is actually when you have no data at all. So you actually develop BBNs from expert judgment. Therefore, there the issue is the algorithm. What the algorithm does is, okay, you know, I cannot ask 1,000 conditional probability distributions. So the algorithm tells me smart ways of asking, smart ways of positioning the questions to the experts, and therefore the algorithms fills in the rest in the most effective way. And this is what I mostly have done. In between, there's a region which I have very little data, but the data doesn't go where that algorithm wants. You know, the data is where the data is. So you need to have a flexible algorithm that goes, you know, where the data goes, and then fills the rest, not based on necessarily where you want the experts to tell you your story. So that's the originating thought. Now, the first work that we did, now we are working on improving that. It's very rough, if you will. So we assume that, okay, you know, these are the conditional probability distributions that we needed to have. And we are going, for example, to look at this little aspect here. So we will need to fill in this table with conditional probability distributions, if you want. So our first assumption is that we only know values at some anchor position that we call. So which are the extremes? This is the most simplified position. So, you know, at the extremes, and then we need to fill in what lies in between. Of course, it's not very smart because, again, you know, you need to have all the extremes. All the extremes is 2 at the power n of how many extremes you have, which was okay for this model because in the end we needed 25 anchors. But, you know, as the model grow with many inputs, then this will become intractable. And this is something that we are working currently, and I might give you some hints, but we don't have results ready yet. And okay, what we were working on is what we did was, okay, you know, we approximate these anchors with distributions. We assume these are normal distributions. Then we take the mean, we take the sigma, and then we take the mean and the sigma of these points, and then we interpolate what's in between. So quite, oops, I'm missing one slide. So we interpolate what's in between, and get what the values are. You know, you assume this is 1, this is 2, this is 2, and this is 4, and then you get all the missing values. I used to have a slide with the missing, but I thought it was a duplicate, and you know, 1 minute before connected, I canceled it. But anyway, you got what the concept was. Anyway, I'm short of time, so it's okay to have one slide less. The concept was, okay, you know, here I was interested in the anchors. Some of the anchors we could get from the data, but some other anchors we couldn't. So we could use anchors from the data, and then others, including them from expert judgment, and then fill in what the algorithm satisfying the input of the algorithm. And we were still using the same Bayesian approach, basically, to develop the conditional probability distributions from where we had information, whether it's expert judgment, which meant us, or the database. And then in the end, what got as a global results. I think what also, for the sake of time, what is interesting is to see what came up. What came up is, that's what the first BBN looks like. So here we're using anchors, as I showed you, at the extremes. Anchors at the extreme, some were this database one, from the early 2000s, and some of the expert judgment. Running this interpolation, getting this. Uncertainty is very large. Of course, we don't have a lot of information. Database one actually says, for this specific assessment, says that error forcing impact is high. So the prediction is actually quite off. But the reason is because this event was not used in the learning. I said, the database was split between what matches the anchors and what doesn't match the anchor. So we're using what matches the anchor, run the algorithm, and then compare with what the non-anchors were saying. And this is again so the idea underlying was doing this. So, we have a database plus expert judgment, getting anchors, running the fitting algorithm, and get some sort of prior BBN. Then take the whole database. The whole database would match positions that are not in the anchors, and then we would use again this Bayesian update on the conditional probability distributions to fine-tune the specific conditional probability distribution hit by the new database, eventually rerun the filling on a local way. And this is something that we are also working now to improve, and then get what we call this posterior 1 BBN, and then our validations. We're using the first data set, the one in the early 2000, but then we have two databases, and we wanted to see if the BBN learned on the first database was sort of matching a different expert in a way, because I was mostly involved in the second analysis of operational events. Other people were on the first set of operational events, so we wanted to see how the two compares. These are results on events on the first database. This is the predictions of the Bayesian belief network from the algorithm, knowing only the anchors, and you can see that the crosses are what the BBN says, the error forcing impact, most likely error forcing impact from the BBN. Square is what the database was saying. If the cross goes on the square, I'm happy. If the cross doesn't go on the square, I'm not. And the bounds are also the bounds of the BBN prediction. We can see, except for 4 cases, not that many, much of the error forcing impact prediction is within the 50 confidence bound, which is okay, what we expect from the 50 confidence bounds. Prediction error for 7 cases out of whatever they are, which is not very good, but some of these numbers are not coming from, we didn't use them as anchors from the algorithm. So we are only as data from the algorithm. Now we re-update the conditional probability distribution with, again, typical Bayesian update. And then we rerun the interpolation only locally to, this becomes piecewise interpolation and not over the full range of the conditional probability distributions. And this is what we get. This was before and now it's after. Uncertainty goes down, as you would expect, because I got more information. Some that were not well predicted became better predicted. Then we got some other strange mechanism. Some that were well predicted became less predicted because, okay, the data is also not, and we understood what the problem was because this was an outlier and the the data was actually moving the BBN in a different way, but that was what the result was. And now skipping to the, yes, for the sake of time, skipping to the second set, now we had a new set of events. And again, we compared, we basically did the same thing and getting to, again, this is the final BBN built on database 1 and database 2. And we can again see that most of the predictions are within the 50% bounds, some are out, but of course, that's within the expected error that we would want. What I wanted to, I wanted to close. One aspect is, I didn't mention that, is stressed on validation, but it's traceability. We try to, the reason why we developed this algorithm, or the underlying idea of the algorithm, is to transfer the expert judgment not in the building of the BBN, so not directly on developing the conditional probability distributions, but on the database. So the judgment is on the database. It's on whether the situation, whether the factors analyzed in the situation are, the output of the situation given the set of the factors characterizing the situation. And then the rest of the process, we wanted to have it automatic. So that becomes more traceable because you can compare judgment on specific situations as opposed to on developing the conditional probability distribution. So that's what we wanted to obtain. The latest work on the BBN is on this paper. You have all the paper at the end. This includes the data. So if you want to develop alternatives on the models, or even we're working together on developing an alternative BBN or an alternative algorithm, we would be very happy to do this. Currently, we're working on upgrading this interpolation method. We see that one of the issues is that basically the interpolation is it's working well at the extreme, but when you get to the intermediate points, this is still requires entering manually into where to interpret. I don't want to go too much into where to interpret. So we wanted to frame an automatic, wanted to find a way to automatically find the parameters of the conditional probability distributions. So we're working on constraint optimization. We wanted to find we formulate an optimization problem in which we find the optimal parameters that allow optimal prediction of the output of the database input, constrained on some other types of statements that the expert would give. For example, ranking or more qualitative information type. So that's what we're going on. So I think I went very much longer than what I thought, but that's what it is. What it is. I think the take home, you know this stuff. So that's what I'm closing now. So thank you for the attention, and hope it was useful. And of course, if you, I don't know how much time there is to discuss, but anyway, you can reach me for any comments and discussions. I'm really available, even if it doesn't happen now.
Yes,